Hello, good afternoon. I'm going to re-record my master's thesis presentation for making it public. I also make the presentation file available for all to see. I'm going to record the video again to explain it more elaborately. From the presentation first slide, you can see the title. The title of my thesis is Investigating the Techniques to Detect and Reduce Bug-Inducing Commits During Change Operation in Software System. I am Mohammad Nadeem. I work under the supervision of Dr. Chancellor Roy in Software Research Lab, Department of Computer Science, University of Saskatchewan, Canada. So, in this thesis, I included 3 of my studies. Actually, the studies are 4, and I combined 2 studies in the first study for the convenience of writing, because both are very similar. Both are very similar studies, and the second and third study. The main motivation for doing the studies was to, as we know that bug-inducing commits creates much problem in the software development industry, and most of the available studies are trying to solve the problem. And I also wanted to contribute in solving those problems, because if these types of studies are going in a right direction, or everyone, if as many as we can contribute in these types of studies, the software systems will be very easily maintainable. Reliability will increase, and also it will contribute to making the software systems less costly. So what I did here. Here I am showing a sample data sets with 5 commits. Among them, 2 commits are labeled as bug-inducing, and 3 of them are non-bug-inducing. And in the data table heading, you can see that there are some table columns such as depth of inheritance tree, line of code, comment density, total number of directories. Those are the quality metric values which I have extracted using a tool, and put the quality metric values against each commit ID to represent the commits. Now, if I train a machine learning model using this data, the model will be able to detect a future commit as it is bug-inducing or not, based on the trained data provided. Here I want to show an example of decision tree classifier which is trained similar 63 data samples. And to classify the 63 data samples, the decision tree classifier now using some of the feature values in its classification node, and based on the feature value, it will decide that the commit is true, means bug inducing, or false based on the value. If in this node it comes true, it will declare that the commit is not bug inducing, and if it comes false, then it will again check the another feature value, and if it comes true, then it will tell that it is not bug inducing, and it becomes false, then it will declare that the commit is bug inducing. In this way, every new commit's feature values will be used in this decision tree classifier, and thus it will able to determine the new commits as bug inducing or not. We can evaluate its efficiency with providing some known data sets, and what I did in this study that I tried to evaluate that based on these feature values extracted from the source code quality metric, how efficiently machine learning algorithms determining the bug-inducing commits and non-bug-inducing commits from the test datasets. One thing here we can see that the decision tree classifier are classifying based on only two feature values, which means this decision tree classifier prioritizing all the feature values and finding these two feature values as important one to be used here. Based on the change in the amount of data sets, the available feature values, the number of prioritized features may change. But one common pattern, what I experienced in this study is that if we have a larger data sets, then the amount of feature values will be larger because to classify them. As there is a 63 data samples, this decision tree can able to classify all the find a pattern in the data values in these two feature values, and it is able to classify them using only these two feature value. So if now if a new data instance is available, then based on these two values of the ns, which ns and number of setters and TNDI, total number of directories based on these two values, it will determine that first the new commit is not bug inducing and the second one is bug inducing. In the first and second study of my thesis, I have used these three machine learning algorithms and investigated the results and reported the findings based on the results. So I am going to briefly explain the first study, which is actually the combination of two studies. And the data set, what I have extracted in these studies are from the GitHub statistical value of the software system, which are in the 4 categories. And the total number of these feature values are 12. And these types of feature values are most commonly used feature value in similar kind of study. I have extracted those values for comparing my new feature added features, how my feature is performing better or worse compared to these feature values. So my one kind of feature is keyword count. What I did in the first study, that my software systems are Java-based software systems. So in Java, there are 51 keywords. That means I have counted the number of every keyword in the source code of the commit patch and used this counted value as a feature value in the representing the commits to be used in the machine learning models. Another type of feature what I have used here is total 743 features. I have extracted those features using a software tool, SourceMeter, which is available in this link. And those features are in these 6 categories. And this represents different kinds of quality metric values, source code quality metric values. I given the short name SM in the studies, and which are the complexity metrics, which represents the how much complexity in this particular revision of the software system. That means before the commit, every commit making a new revision of the software system, and while doing a commit, how much complex was the source code of that particular revision. Similarly, the coupling metrics are extracted, cohesion metrics extracted, and the other 3 metrics are extracted, and those 743 values are then used to represent the commits in our dataset. So the goal of the first study was this too, where I have applied a data filtering technique and come to deal with the data imbalance, as we know that in machine learning models, data imbalance is a big problem. And if data set is not properly balanced, machine learning models results are not we could not find a good result from the training a model with that imbalanced data sets. And I also wanted to see whether the source code quality metric values doing some contribution in detecting those bug inducing commits. Now what I'm meaning about the tool-based data sets filtering. Well, let consider that there is a software system which was working good, but someone did a commit, and after doing that commit, software systems becomes buggy. Now, what would be the next step? The bugs should be identified, reported, and identified, and should be fixed. So, if we want to train a machine learning model to detect those bug-inducing commits, we need another set of data to provide the machine learning model as a negative example. This data will be the positive example, and this data will be the negative example. And based on this data, machine learning model will train itself to detect these examples from the future commit. So, but here we can see that usually this bug-inducing commits data remains very small in number, and all the other commits remain in very large in number of samples. So in our investigated Jenkins datasets, only 4.27% was the bug-inducing commits, and the remaining 95.73% was the other commit. So if we consider this 4.27% as the positive data sample and all the other 95.73% as the negative data sample, this will create a largely imbalanced data set, and based on the training, those imbalanced data sets, the model will not perform very good. A recent study published in 2019 in a workshop with ESC shows that using these highly imbalanced data sets, they get only 2% of F1 score for detecting bug-inducing commits or for just-in-time defect prediction. They actually discuss the term just-in-time defect prediction, and I'm telling the term bug-inducing commits. Both are actually same in the literature. Just-in-time defect prediction is mainly done by detecting the bugs during the commit time. So I am telling the same thing, bug-inducing commit. So they also showed that if they provide upsampling by SMOT, also do the downsampling of the majority class by cluster centroid, or combine both up and down sampling by SMOT plus TOMEC. TOMEC is a downsampling technique. SMOT is an upsampling technique. So they combined both, and they did several implementations, and from those implementations, their best result is this. So, which is only 13%, and they also mentioned in their study that this is not any performance which could be used in practical cases. So what we can do? So the problem is we need to train the machine learning model to detect the bug-inducing commits. Now we have another types of commit, which is bug fixing commits. And the basic characteristics of bug inducing and bug fixing commits are bug inducing a problem in the software system, and bug fixing commits fixing that problem. That means removing the same problem from the software system. So those two commits are totally different to each other, which means if we disregard all the other types of commits and provide the bug-inducing commits as a positive data samples we are trying to detect using the machine learning model, and provide the bug fixing commit which do not induce new bug in the software system as the negative data sample, then the imbalance will be imbalance will be much reduced, and the machine learning models will provide better accuracy in detecting those commits. Though the imbalance in datasets are not totally removed, but we find much improved result, and we added in this study two types of features. One was the commit keyword count and the source meter based feature. Inclusion of those features with GitHub based features enhances the bug inducing commit detection accuracy. But we also see that the commit count and source code meter based features improvement is not much bigger, and also they alone cannot detect the bug inducing commits, which I found in our results. So we motivated to do more investigation with source code related bug inducing commit detection and did our second study. So what was the second study? In the second study, I tried to find out the code pattern, which might be the availability of particular code pattern is responsible or could be used in detecting bug-inducing commits or not. So in the second study, the steps of this studies are this, where I used manually labeled datasets from 6 software systems and extracted their code, cloned the 6 software systems from their respective GitHub repositories, extracted the GitHub statistics based features. These features are same as extracted in the first study. Token pattern, this is the new feature which I have extracted in this study. And token sequence, that means sequence of all the tokens from the token pattern. This is another new features used in this study, and I ranked those features, applied the classification algorithm, and investigated, compared, and reported the results. So the goal in this study was to determine that whether those token sequence and token pattern based features are contributing to detect those bug inducing commits along with the GitHub features or independently or not. With GitHub features and independence. So here my focus was to verify that token sequence and token pattern should detect the bug-inducing commits using the machine learning models with or without the GitHub features, and how the performance are improving. And also the improvement of the performance is statistically significant or not. To test the statistical significant, I did Wilcoxon signed rank test. So, well, what is the code pattern trying to extract from the source code? Here, two code snippets are shown as an example. The motive to write both the code snippets are same, but they are written into different pattern. That means this is a common scenario if two different software developer doing writing the same functionality, they will write in two different way. Especially if the functionality is not very common or they are complex or large. So the target in this study was to investigate whether this difference in the coding patterns is making any difference in detecting the bug-inducing commits using the machine learning model or not. To do so, I have used here a tool. The name of the tool is SourceML, and first converted the source code with an XML format. The SourceML does it. We have to use it. We have to use this tool to convert the source code. After converted, here I have shown the simplified version of the converted XML format. That means the actual converted XML could maybe quite complex depending on the source code. And I have to be providing an idea how the token patterns or how the code patterns are actually look alike. I have provided here a simplified version of it, where we can see that if is given a common name, if condition, X is given a common name, equal operator is given a common tag, and also number is given a common tag. And under this if statement, there are two other statements, and this statement can also be expanded like to that. And there's the two code snippets has two different patterns. The XML patterns are also different. And from this from the token names of this XML pattern, I have extracted all the sequence of the tokens and then counted the token patterns in the commit source code of the commit page. If from each, how many similar token patterns have been extracted from the commit page, and also did an n-gram based bag of work, which is mainly used in natural language processing techniques, and made these two values will be then used to form a data sets representing each of the commits. That means in this way, I have made the representation of each commit using the TS and TP values to be used in machine learning models. So here a sample encoding is given. An example of 5 commits are given. Their associated labels are given also. And 1 represents the bug-inducing commits, 0 represents the clean commit, and from each commit, which code patterns are identified are given here. So from here, and so from all the code patterns in our data set, if we find 7 unique patterns, then each of the pattern will be used then a column head to represent the feature names. And under each column here, the count of those patterns. For example, in commit 1, TP3 is 2 times, TP4 is 2 times, and commit 4, TP4 is 3 times. Those counts are put, and those are not available are put obtained 0. That means 0 represents those patterns are not available in the commit, and the subsequent number represents that those patterns are available in the commit. Now this dataset could be applied to detect those bug-inducing and clean commits using the machine learning models. Here the subject systems, there is a 6 subject systems available, and those the data set labeling, that means the identification of bug inducing and clean commits are done using an study published in ESC FSC 2019 by Wen et al. They published these data sets from the manual investigation, and they also showed that this identification of bug-inducing and bug-inducing commits are usually done using the SJZ algorithm, but they also showed that the number of identified bug-inducing commits using the SRLab algorithms are not reliable in their investigated 63.7% of the cases. And as I am going to evaluate the token sequence and token pattern based representation, if token pair sequence and token pattern based features effectiveness to detect the bug inducing commits, I used those manually investigated datasets, which seems reliable to me. Here, the distribution of the result is given in terms of F1 score. We know, I think all we know that what is F1 score. I first calculated the recall, calculated the precision of each of the chapters in each of the dataset, used datasets, and then from the precision recall, I obtained the F1 score. And there are two primary features are GitHub based features, token sequence based features, and token pattern based features. And all these features are prioritized features. Here, GitHub all represents all the features. That means prioritize, non-prioritize, all the features. And I mentioned in earlier slides that I extracted 12 features from GitHub. All 12 features are here, and some features are removed here, which seems not important by random feature elimination process. And here also the features are removed. Those also the combination of those features, but the remove the non-important features. That which means these all the features are prioritized features. Only the important features are taken, and here all the important and unimportant features from GitHub are taken. From the distribution of F1 score, we can see that this distribution shows the lower values than all the other distribution. And from also here, we can see token sequence shows much upper distribution. And I also did the significance test using the Wilcoxon signed rank test and calculated the significance of bug-inducing commit detection of each of the precision, recall, and F1 score. While considering the precision, which shows that the non-prioritized features with the prioritized, all the prioritized features result are significantly better than the non-prioritized features result. And while considering the recall, the token pattern, and inclusion of token pattern with GitHub statistics are significantly better than prioritized and non-prioritized both in both senior cases, GitHub and GitHub-based features. And while considering the F1 score, again, there are two types of results. One is the one shows that all prioritized features are significantly better than the non-prioritized features. And also, if we add token pattern with GitHub statistics value, then it becomes significantly better than the results obtained by only GitHub-based features. From the study 2, the basic findings of this study is I show that in this investigated subject systems, the token patterns or software code pattern based features perform significantly better than the significantly better in detecting bug-inducing commit. Now, as inclusion of code pattern based features improves the bug-inducing commit detection performance, and it also can detect the bug-inducing commits independently, which means that the commit patterns provide the number of the such commit patterns providing the information to the machine learning models that how the bug-inducing commits should be identified. And in my future work, I will try to detect particularly what kind of commit pattern are responsible for inducing the bug-inducing commits, and also try to make do and what to do and what to not to do for software pattern for software developer. That means there should be a pattern guideline for the software developer if you want to minimize the number of such occurred bug-inducing commits from the software system. That means we need to make a pattern guideline for software developer, and making such pattern guideline for software developer is in my future study, immediate future study, and I will try to start that study as soon as I can. And in based on the results from the first and two studies, I get motivated to do the third study, where the intention of doing the third study is to the scenario that how we could eliminate or reduce the number of such occurrences of bug-inducing commits. To do so, I did an evaluation of clone detection tools, where in detecting cloned co-change candidate and the detection of cloned co-change candidate during changing in the software system can reduce the to help to avoid the occurrence of inconsistencies or bug from the software system. How it can be possible? Let here C1 to Cn, there are n changes happened in a commit operation of a software system. Now, if C1 is a change, target change, then all the other changes are the co-change. Again, if C4 is the target change, then all the other changes are the co-change. And if all the other co-change is not changing with the target change, this is called inconsistent change. And earlier studies show that the inconsistent change induce bug or fault in the software system, and in their investigation they found that in 3 to 23% of their cases it induces faults. Another earlier study also showed that the inclusion of clone detection tools, such as they included NiCad, in change impact analysis tool, can enhance the performance of change impact analysis. Change impact analysis is also the finding the co-change candidate, but they did not compare the other tools and to find the which clone detection tool are good for that. For that reason, I did the comparison of some good clone detection tools in this study and try to determine that which clone detection tools could be good to be used in these types of study. To do so, we need to evaluate the clone detection tools and how I evaluated them. Let's again consider there are 5 changes, C1 to C5, and C1 is a target change, then the other changes are the co-change, and there are 4 clone fragments detected by a clone detection tool in a clone class. So F1 is a F1 intersecting with C1, which means F2 to F4 should be the co-change. From the clone detection tools result, we are predicting there's 3 clone fragments from the result. So now I have now the target is to evaluate that how efficient this prediction is. Here I predict the result is predicted 3 clone fragment as a co-change. Now which fragments are intersect with actual co-change? If we find that F3 and F4 intersect with actual 2 co-changes, which means this detailed prediction is correct, and we failed to predict the other co-changes. That means our actual co-changes are 4. I have predicted 3, and among these 3, 2 are correct. From this value, we can determine the recall, precision, and F1 score. And with the calculating similar values of all the changes in all the subject systems in this study, where I have finally evaluated the clone detection tools. These are the 8 subject systems I used in this investigation. And during selecting the subject systems, I tried to add from different varieties of domain. Also, they should have varieties, the number of revisions. Some are smaller, some are very larger, having very large revisions, and included 2 programming languages, C and Java, as they are most popular programming language for doing the types of software systems, for writing the source code of most software systems. Here is the result of our investigation. Again, the box plot which shows the distribution of F1 score, and this is the actual rank list of our 12 investigated clone detection tools, where there are actually 9 clone detection tools, and CloneWorks have 4 separate configurations: type 3 pattern, type 3 token, type 3 blind, and type 1, CloneWorks type 1. This for making the 4 separate configuration of CloneWorks, total implementation of clone detection tools become 12. Here we can see that the CloneWorks type 3 patterns F1 score distribution is very higher compared to the others, and also we all can see that the text similarity based clone tools do not performing very good in this investigation. Token extraction based tools provides remains the intermediate stage, but abstract syntax tree based, vector based, or pattern based clone detection tools performs very good. Also, we can also see that the clone detection tools with detects all types of clones, subsets type 1, type 2, type 3 clones, clone fragment, they also performing very good. The clone performing very good. Where I also did the significant test. Here the result of significant test in the screen, where the significance of the result of each of the clone detection tools is tested against the all 11 clone detection tool implementation. For example, here 12 clone detection tool have been applied in this investigation. So if we want to see that CloneWorks type 3 pattern is working significantly good than the other or not, then there are other 11 tools, and what we can see, CloneWorks type 3 pattern significantly better, works significantly better in based on the Wilcoxon signed rank test than the other 10 clone detection tools. These are the list. CloneWorks type 3 token also performs significantly better than the other 8 clone detection tools. Similarly, Descartes by the other 7 and CC Finder by the other 6. And from this significant test result, we can conclude that these 4 clone detection tools results are significantly good than the other compared to the other clone detection tools result. So we can conclude that these clone detection tools could be used or could be more investigated in change impact analysis types of research or studies. And I have plans to do the such studies in near future. Now I am going to conclude my presentation where I did mainly two. I focused on two problems. One is the detecting bug-inducing commits, and the other is how we can reduce the number of such commits from the software system. I also represented and investigated the scenario of encoding source code, which can be used in machine learning models. I compared different types of features and their performance in detecting bug-inducing commits. And I also tried to find out the set of best clone detection tools in determining the co-change candidates, which can eventually reduce the number of bug-inducing commits. Here, some future plans included, where I first want to do some TF-IDF or the other types of calculation, as I just included the count-based calculation of token pattern. I want to include some other types of calculation to see whether it is changing the efficiency or performance measures or not. I want to include more clone detection tools in these investigations, and also want to include the software systems of more sizes, more different programming languages, as I just included investigated C and Java-based software systems in these studies. In my future, I want to add some different types of programming language such as Python, C#, or other JavaScript or other types of popular programming languages in this investigation. This is the entire completion of my presentation. Thank you very much for providing your kind attention.